this doesn't go through exhaustively all of the possible combinations, but hopefully this has enough of the getting started type of info for building, the majority of codes that you might come across. And so specifically, this walks through some C and C++ examples with SYCL and OpenMP for GPUs with MPI enabled. I didn't go through a Fortran example, but it similarly straightforward. And then at the very end is some discussion on affinities. Um, and the conversation with the affinities is really meant to be a conversation starter, not an extreme deep dive. And so I'll say more about that when I get to it, but to try to set the stage of getting started. Um, on Aurora, for compiling codes, and really this should be a Fortran as well as I catch things that need to be fixed. We're using what look like the traditional NPitch wrappers, and so MPI CC will give us access to the C compiler, MPI CXX for the C++ compiler, MPI F90 for the Fortran compiler. In the default environment, we're using the Intel set of compilers, and so these are compilers that are based on LLVM, but specifically that they have the optimizations for the CPUs and they support the programming models for the GPUs. And so ICX, ICPX, IFX. These are I think these are by far the compilers that you're going to want to use to leverage the resources on Aurora. Uh, in the simple example, this is just a very simple CPU hello world example, nothing fancy. You can build this code on the login node. You can build it on the compute node. There's no restrictions in that sense. And so simply the name of the MPI wrapper for C++, the name of the source file, dash O in the example. So very, straightforward if you're accustomed to the GNU and Intel compilers. And so that compiled pretty straightforwardly. And I now have an O1 example executable. And that's what the screenshot is walking through what I just did. And so you could run, where is it at? Sorry. So if you just ran that executable, because again, I'm on an interactive job right now. One process, it says hello world. If I ran with six, I would get six processes all saying hello world. And so very simple. Um, Now, in walking through, how to target code that's, how to compile code that's targeting the GPUs. The first example is with OpenMP, and then SYCL will be the next example. Uh, an important detail here with the Intel compilers for GPUs is users making a decision of doing, just like CPU code, the GPU code needs to be compiled. Uh, you can do that compilation either ahead of time when you go to during the traditional building, compiling, and then leaking an application, you can compile the GPU kernel then, or you can delay that until you runtime, where you're actually running your code on the node. Uh, there are some cases where applications need that runtime capability, the just-in-time compilation. Uh, I think by the majority of folks, they don't need that capability, and so you can just do the ahead of time compilation. I'll say that if you're not aware of the code that you're using and you've never heard of just-in-time compilation before and your code has run fine elsewhere, you can probably safely default to ahead of time. And if there's any issues in you know should you use one or the other, this is a good conversation point to send a ticket to support. Um, and so my default is doing a ahead of time compilation. And so for targeting OpenMP for the GPUs, we would use dash FI OpenMP and then dash F OpenMP targets, Spear 64 gen. And so generating the necessary code for the GPU kernels. And then the link line is the same with those first two flags. And then we're additionally specify what architecture are we compiling the GPU code for. And so in this case, we're targeting the PVC GPU. Um, and so, you'll notice when you go to link your application that the linking step may take a little bit longer. And that's because this additional compilation pass for the GPU kernels is occurring. Uh, if you, for what one reason or another, you prefer to do the GPU kernel compilation later during runtime, when the code is actually running on the node with those devices, those flags here are here. And so instead of Spear 64 Gen, you would just type Spear 64, and you don't need to declare the target device because that'll be detected automatically when you go to run your application. And so really the trade-off from well, one perspective is you can pay a one-time cost for compiling that GPU code when you're linking the application like you would traditionally would, or you would pay that cost most times when you run the application. And so if those code kernels weren't cached, for example, you'd have to recompile them every time. And so I really, if you don't are not familiar with just-in-time compilation or your application, doesn't require that, I would stick with ALT ahead of time to start off with. Um, and so you can just type, the commands here for a simple example, the O1 example, OpenMP. Um, you can copy and paste this line to do the compilation step, and then you can follow up and copy and paste this to do the link step. Uh, this is a really simple example, and so it doesn't really need to be split out into the compilation phase and the link phase, but as a way to provide instruction for building bigger applications, we break it out this way. Uh, the submit script, it looks very similar as the earlier example. Uh, there is the use of this PBSO work directory, and so that's maybe a convenience that this by default PBS scripts will start up in your home directory. And so whether you encode an absolute path that you change into, or you ask for it to change into the PBS work directory wherever the Q sub command was submitted, you want your script to run from the correct directory. And so that's just an important thing to be mindful of. And so having this here will change into whatever directory the Q sub command was launched from. And then you can similarly, run the Q sub command, specifying the allocation and the queue, if you want it to be something that's different than debug. And I'm kind of going, I don't, I'm kind of going through this to stay on time. Sorry. Uh, when that code runs, you'll see if you submitted it as a batch job, you'll see the log files in that logs directory. Then you'll see some simple output that, the code detected that there were 6 devices, and it ran a very simple test on them. And hopefully everyone sees that the result is correct. Uh, the sickle example is exactly analogous. Again, there is a choice of doing just in time or ahead of time compilation. I'd advocate for ahead of time compilation unless you have a particular needs. And so here the flags are a little different. Dash dash Intel to do an Intel pass over the code generation. Dash F sickle, and then we're specifying the target. And so just like with OpenMP, we specified the sickle target as Sphere 64 underscore gen. And similarly, we also specify that we're targeting the PVC device. Uh, if you opt for the just-in-time compilation, then you can leave off the device specification. That'll get determined automatically. Um, Again, the example, here's the compile line, here's the link line. And so these are commands that you can copy and paste into your terminal and execute to compile the code and then run the code using the example submit scripts here. And then what I want to spend
Yeah, I
the
thought it's going to worse, but it's fine. That's not too bad. Yeah.
was it okay. I don't
So
know
we
if
have a
that's
quiz on Friday
Yeah.
I'm sorry, let me just see if I can mute it.
over just cues and
all
Okay.
right. So I want to I'm not going to give this justice. I apologize in the 5 minutes, but these are commands that everyone can run and you can look at and you can, think about how to map this information onto your application. And so again, one thing I want to really impress upon is that yes, we have very powerful GPUs and we have a lot of them on each node. We also have a lot of CPU resources, and while I don't think it's necessary to correctly map out processes on the CPU side on day one, you really want to think about that for performance, especially as you scale up and start using communicating data between nodes. And so whether it's initially or soon after, this is going to be something that you want to think about and discuss with us. Uh, on the compute node, if you run the list CPU command, you'll see information about the CPUs that are sitting there. Really, the important thing is that there's four NUMA domains. Two of the first two of those domains are the CPUs themselves with the DDR memory. These other two NUMA domains, those are the HBMs. And so, really, and so a key thing here is that cores 0 through 51, those are the physical cores for that first CPU. These are the core IDs that you're going to want to bind processes to. Uh, 52 through 103, those are the core IDs for the CPU in the second socket. Uh, you'll be want to be mindful of binding processes to specific sets. You don't want to spread across NUMA domains, for example, and the performance impacts that might have. Uh, if you can see a little bit more information with the NUMA control command. And if you ask for the hardware, you can then again see that in NUMA node 0, uh, all of the CPUs are here listed out, in the full list. And then you can see the that node 2 and 3, these are the
Chris, may I have a quick questions? Is this
super
true?
quick. Yeah.
Uh, is it true that you have the hyper-threading, the hardware threads turned on?
Yes, they're there.
They're there, right? It's
Yeah.
two, right? Two
Yes.
threads.
Yeah. So
Yeah.
0 to 51 is what I would prefer to bind your initial process. And if you
Mhm,
wanted to bind a second task to each of those cores, you would use the CPU IDs 104 to 155, for example.
mhm. So there's no impact on the performance of, let's say, hybrid MPI of OpenMP code in this case at all?
These are not physical threads, these are the hyper threads, and so there will be an impact, but that's very application dependent.
Uh, so for the application that you have tested, there's none impact, let's say, discernible.
I don't like hyper threads. I don't use hyper threads. I tend to see a negative impact.
Okay, so there's no way to turn off. If I know that my application won't be negatively
Oh,
impacted.
I when I'm speaking to only binding processes to the physical cores.
Ah, okay.
I
I
would
see.
not bind additional processes.
Okay, okay, cool. Thank you,
But
guys.
again, this is very application specific.
Mhm. Okay,
And so
thank
if
you.
yeah, if you have a lot of lightweight CPU tasks and you have many of them and maybe latency limited, that may be a very good candidate for making use of hyperthreading.
Mhm.
If your CPU tasks are doing something very compute intensive or driving memory bandwidth on the CPU side, you it's probably already fully leveraging the resources in that core, and a second thread will just get in the way. Um, um, okay. And so there's a couple of commands. You can see a lot of detail on the hardware that's available on the node. And so these are useful if you don't want to keep going, say, to the AOCF documentation to look up details. It's available there on the node. Um, and so day one, uh, you may be focused more on the GPU performance. And so for the CPU side, you could, for example, if you want to run 6 tasks, maybe one per GPU, you could just naively use a simple depth logic where in this example, depth of 4 is you want 4 cores for every MPI rank. And so the very first MPI rank will be bound to core 0. The next MPI rank will be bound to number 4. And so you can use this very simple CPU binding to just get things going. Uh, Later on, when you start thinking about performance and placing these ranks, on CPU 0 and CPU 1, because you want to make sure you're leveraging the NIC resources and you want to make sure the CPUs are closest to the GPUs and start thinking about those, you may find it more useful to provide an explicit CPU list. Um, on the GPU side, there's additional flexibility, and so people can think that the flexibility is a good thing or a bad thing. Uh, what I encourage is starting slow and building up in complexity. Each of these 6 GPUs on the node physically are 2 tiles with a very fast connection between them. And most applications I think we're finding, or at least most applications I deal with, is finding it beneficial to bind MPI ranks or OpenMP threads to the individual tiles. And so now the application doesn't see the node as having 6 GPUs. It sees the node as having effectively 12 GPUs. Um, and so thinking of how to bind processes evenly across the CPU in those 12 GPU tiles. For some workloads, uh, where maybe you still have a lot of work that's left on the CPU and you need to parallelize over that work on the CPU, you can have those MPI processes target in finer granularity the GPUs. And so you could split the GPUs. So this script is helping to split the GPU into tiles, 2 tiles per GPU. This script is helping to target individual compute command streamers, and so splitting these tiles into half. And so instead of having, this would be an example of 4 MPI ranks per GPU, or you can really go further and have MPI ranks bound to a quarter of a tile. And so depending on the application and the workload, there's lots of flexibility here. And these examples kind of touch on it at a high level and how to explore it. I very much encourage benchmarking, and I very much encourage reaching out to us and discussing this in support. And we're in the process of providing more examples and more guidance, but really this should be driven by the application and the performance that you're seeing to help decide how should you target MPI ranks to the GPUs, and how many threads should you allocate on the CPU side, and so on. Um, and these helper scripts are available. All they really do is it's simple logic that you they look at what MPI rank they are on the node, the local rank ID, and based on that rank, they pick a device. And so right now it's a round robin assignment. Depending on your application, you can easily change that assignment to suit your needs. And so really this is just something to get started with it, to tailoring it to your specific application needs.